This is Mr. Anderson from Kellogg Community College. Today we're going to look at the second part of our review test, and the first thing we're going to do here is see what we can do with this quotient rule. Now it says here, assume all that no radicans were formed by raising negative quantities to even powers. That means if we take the square root, like let's say the square root of 25, then the answer will be just 5 instead of plus or minus 5. So we can see that right now, square root of 7x, there's nothing you can do there. And when I look at the numerator, I see that, well, I can kind of put these together. There's a quotient rule that states that as long as we're under the same radical, you can combine these together. And there's some earlier work done on that in the chapter. So what you have here is 700x divided by 7x. The 700 divided by 7 is just 100. And x divided by x is 1. And the square root of 100 is 10. Now again, because of this statement here, we don't have to consider that as plus or minus 10, which will simplify it, or actually make a lot of our even roots, square roots, fourth roots, sixth roots, not having to think about that situation. In problem 22, this one's pretty quick because dividing these two will just give you 7. 35 divided by 5 is 7. And the cube root of 7 cannot be further simplified. This is a problem too that we can do a little bit of work if we put this all under one radical. 189 divided by 7 is 27. X to the fifth divided by x squared is x cubed, because you have 5 on top, 2 on the bottom. 5 minus 2 is 3. And then we have y to the seventh over y squared is y to the fifth, because 7 minus 2 is 5. Now the cubic root of 27 is perfect because 3 times 3 times 3 is 27. So 3 is the simplified version of the cubic root of 27. 3 goes into 3 once, which means that the cubic root of x cubed is x. And 3 goes into 5 once. So that leaves me with 2 left over, or 2 y's here, under the radical. And a lot of this was talked about earlier in the chapter, so please feel free to watch those videos to get a further explanation of why that's the case. We're going to continue with more problems along that vein. 24 through 26 have that same kind of flow to them, and then we're going to do kind of a gear shift here and switch over to some addition, subtraction, and multiplication of radicals. Therefore, let me just put a line here, and this line is going to kind of separate the differences in all these problems. Alright, now we're going to put this under the same radical here. So let's go put a fifth root in here. 64 divided by 2 is 32. Then 11 minus 2 is 9. And 28 minus negative 2 is 30. So the fifth root of 32, and the fifth root of 32, luckily for us, is 2, because 2 times 2 times 2 times 2 times 2 is 32. 2, 4, 8, 16, 32. So the fifth root of 32 is a whole number. 5 goes into 9 once, with 4 left over. So this is the fifth root of x to the fourth remaining. Now 5 goes into 30 perfectly 6 times, so this would be y to the sixth power. For problem number 65, we're going to see oh wait, there might be something that we can do here. Since this is together, we can see if we can break this up. And sometimes breaking things up, instead of trying to just simplify this, might be the best way to go about it. 64x to the seventh. Now, the cubic root of 64 is actually, we're just doing the top half of the problem right now. Cubic root of 64 is 4. Because here you have a problem where it's 4 times 4 times 4, which gets you up to 64. And 3 goes into 7 twice, so this is x squared, with the cubic root of x left over. Now let's look at the denominator. If we have the cubic root of 216, that's going to be perfect because that's a 6. So here we have the cubic root of 216, which is 6, and the cubic root of y to the sixth, or how many times does 3 go into y to the sixth? It goes in there twice, so there we go. We're going to have y squared. Now, at the end of the problem, notice that 4/6 can be simplified, so this would be 2/3 x squared, and then the cubic root of x. Alright, now taking a look at this problem here, You can blend these together because I think that would actually solve a little bit of some of our problems here. So in the fourth root, we're going to have how many x's? It looks like we got 12 minus 2, which is 10, and negative 14 minus 2, which is going to be negative 16, so that's y to the 16th power in the denominator. And then we have a 16 right there. So how many times does 4 go into 10? It goes in there twice. And what we have is we have 2 x's left over. Over, the fourth root of 16 is 2, because 2 times 2 times 2 times 2 is 16. 2, 4, 8, 16 if you multiplied those. And then 4 goes into 16 4 times perfectly, so y to the 4th power. Okay, so now what we're about to do is we're about to take a look at the next quote-unquote, this is like a next section of our work here, where on some previous notes, what we did is we had the addition and subtraction of radicals. And in that section, I emphasized that if you had like 14x minus 8x, then you get an answer of 6x. And that's kind of the way you have to think about these kind of radicals, because I'm going to circle these radicals because they're exactly the same. So you treat them like variables if you're adding or subtracting them. So this is like 14x minus 8x, which would give you 6x, or 14 circles minus 8 circles gives you 6 circles, or in this case the circle would represent the fifth root of 2. So that would be your answer to number 27. Now I can't actually circle these two numbers together because the square root of 50 and the square root of 2 are different. So what I'm going to do is look at the square root of 50 and see if I can break that down. Using our work from the third section of our chapter, we can see that we can take the 50 and divide that by 25 and 2. And we should always look for ways to break down a radical into as small radical as possible. So the 9 is still there, so this becomes 9 times 5 times square root of 2, or 45 times square root of 2, minus 4 times square root of 2. Now you can see that the square root of 2's are the same, so I'm going to circle those. So this is like saying 45 circles minus 4 circles would be 41 circles, and the circle represents square root of 2. And the same thing's going to hold true, but if you take a look at number 29 here, we're going to do something similar to what we just did in this problem. The cubic root of 54 doesn't actually have a nice, easy, break for that. But what we can do is make that into the cubic root of 27 times the cubic root of 2x. And the reason why I put the cubic root of 2x together is because the cubic root of 2 does nothing. You can't actually extract something out of it. So what we're going to do here is take the cubic root of 27, which is 3, and multiply that by the cubic root of 2x. Now, in our second part of the problem, the cubic root of 2 can't do anything, but 3 can go into 4 once. So that lets me extract an x, or factor it out, or take it out of the problem, and then leave inside here 2x. And as you see, if I bring this down one more step to line it up with what I did on the other side, you can see that now I have, look at that, the cubic root of 2x in both of these places. So we're going to factor that out, so we'll get 3 minus x times the cubic root of 2x. Now, we're going to take a break from addition and subtraction, and we're going to do some good old-fashioned distribution. Now, to do distribution, you're going to look at the number in front of the radical and also the number inside of the radical. Notice these are all the same. These are all square roots, these are all cube roots, and so on and so forth. We're not going to be mixing radical indexes inside of the same problem. So 4 times 1 is just 4, and square root of 2, square root of 3 is square root of 6. 4 times this is also 4, because notice these have 1's in front of them. So square root of 2 times square root of 5 is square root of 10, because you can multiply inside. This is the quotient rule here. If you have square root of 2 times square root of 5, you can bring those together in the same radical and multiply those together. Now, this is an acceptable answer. Some people might factor out a 4. I think if you don't know what you're doing, this might lead you into trouble because you might think this is the square root of 16. You cannot combine these two. You cannot combine the square root of 6 plus the square root of 10. You can't do that, just like you can't say x plus y is the same as thing as xy. You can't just turn addition into multiplication. So this is actually done at either step. I just wanted to show you that. Now since this is 1 in front, we're going to do a little distribution here. So this is 1 square root of 8. And 1 times negative 2 is negative 2. 2 times 32 under the cubic root is going to be 64. This gives me 2 times, or the cubic root of 8 is 2. The cubic root of 64 is 4. Now be careful to remember your order of operations. I don't want to see a lot of people putting 0 on this test, because 2 times 4 is 8, and 2 minus 8 is negative 6. So please, please, please make sure that's there. Okay, so 32. Let's do some FOIL here. So here's our first, outside, inside, last. Okay, so 4 times 2 is 8. 4 times square root of 5 is, well, 4 square root of 5. 2 times negative square root of 5 is negative 2 square root of 5. And negative square root of 5 times positive square root of 5 is negative square root of 25. This leaves me with 8. Move these two together. This is going to be positive 2 square roots of 5 minus 5. Then 8 minus 5 is 3 plus 2 square root of 5. That is the format of this problem, and if you've done the later sections of homework, we always keep our format a plus bi, so put the whole number first and then put next to that the radicals and imaginary numbers afterwards. To continue on with this idea of FOIL, we have a couple more problems here. Let's rock this FOIL problem here. And we're going to distribute there. So this is going to be 8 times the square root of 25. This here is going to be 16 times square root of 10. This here is going to be negative 6 times square root of 10. And this here is going to be negative 12 times the square root of 4. Now 8 times the square root of 25 is the same thing as saying 8 times 5, which is 40. The negative 12 square root of 4 is the same thing as saying negative 12 times 2, so this is negative 24. We'll be putting these two numbers together. These middle two terms, 16 minus 6 is 10, square root of 10. There's nothing else you can do with that, and the 10s stay the same because, again, like variables, if you had 16x minus 6x, it would be 10x, or 16 circles minus 6 circles is 10 circles, where the circle is square root of 10. Now 40 minus 24, that's going to give me 16, and plus 10 square root of 10. I like putting number 34 as one of your test questions because I think a lot of people just think they can do that, but you can't. You can't just say 5 minus 3 is 2. You have to write the problem out twice. Square root of 5. Oh, shoot. I put the parenthesis there too early. Let me try this again. Square root of 5 minus square root of 3 times the quantity of square root of 5 minus square root of 3. And we'll do our FOIL. This here is the square root of 25. This here is negative square root of 15. This on the inside is another negative square root of 15. And this last part here is positive square root of 9. Square root of 25 is 5. Minus minus, this is minus 2 square roots of 15. And plus the square root of 9, this is plus 3. 5 plus 3 is 8, minus 2 square root of 15. All right, number 35, this is actually a trick that we will use to get the radical out of the denominator. We're going to do some FOIL here. 3 times 3 is 9. 3 times negative 11 is negative 3 square root of 11. 3 times square root of 11 is positive 3 square root of 11. And finally, the last cable there is going to be the positive times negative is negative square root of 121. So now we have 9. These two simplify to make 0 minus 11, because the square root of 121 is 11. 9 minus 11 is negative 2. Now the reason why I highlight this so much is because when we have a binomial in the denominator, like 3 plus square root of 11, to get rid of that we're going to multiply top and bottom by 3 plus or 3 minus square root of 11. And if we do this, then our denominator would rock to -2. So I'm going to show that to you in the examples before the end of this video. In problem 36, we're going to do a little fun kind of dimension changing here, where we're going to actually combine these. And it seems like it's impossible, but the key is that the bases are the same. So I can turn this into a fraction. It's inside over index. This is for the first fraction here. And this one's going to be also inside power over index. And then what we can do is we can add these together. So this is b to the 4/3 plus 3/4. I've done a little scratch work on the separate piece of paper here, and I do the scratch work because I don't expect the fractions to be something that you and I need to work on. So if I did the work, let me just go check my notes here. Excuse me. I get an answer of 25/12. Because I don't want this video to be about, how can you add a fraction together. I want this to be more about what do you do when you get that done. Well, this is going to be then the 12th root of b to the 25th power. And we got to simplify that because we got to see how many times does 12 go into 25. The answer there is 2. And this also leaves us with one b left over under the 12th root. Oh, okay, you can maybe see over here that this would be 2 and 1/12, and that would convert to this as well. But I kind of like to take my students through the same process we've been doing for the whole unit. We're going to continue along that vein and then start rationalizing some denominators here to finish up this worksheet with problem number 44. So if you're following along with the handouts in class, this would finish us through page 2. So in problem 37, this is going to be x to the 2/3 power over x to the 1/5 power, which means I'm going to subtract these two. So if I'm going to subtract them, and I subtract them because of the quotient rule, that if I have two bases dividing each other, I can take their exponents and subtract them, like that. So let me kind of just go to my scrap work here and make sure I've done the right answer, just quickly doing a check. Alright, so my answer here is going to be x to the 13/15. And this is a little bit easier of an answer because it's not improper. So we have the 15th root of x to the 13th power. In number 28, don't get scared by the binomial here. This is 2x plus 1 raised to the 2/3 power divided by 2x plus 1 to the 2/5 power. Alright, so again, like the previous problem, notice it's 2/3, 1/5. This is just 2/3, 2/5. But again, don't let the binomial freak you out there, because when you do this work here, you're going to get an answer of, let me see here, did I get that answer right? 2/3, 2/5. Yeah, I think I'm on the right track here. I've got 2x plus 1 raised to the 16/15, which means I'm going to have this problem here, the 15th root of 2x plus 1 all raised to the 16th power. Now, one thing is that 15 goes into 16 once, so that's just going to give me a 2x plus 1. And then it's going to leave me with just one of these 2x plus 1s underneath the radical, like so. Whew. Alright. Now to finish up this worksheet, we're going to rationalize some denominators. So let's take a look at 39 through 44. Again, the purpose is that we cannot have a radical in the denominator. So our goal is to multiply these until we get it to a rootable number. Now I'm going to split this one up just because I only want you to focus on the denominator. The square root of 2 is not rootable, but a number that is rootable that's close to 2 is 4, because the square root of 4 is 2. So we're going to multiply the top and bottom by 1, which is basically this whole thing is multiplying by 1, but if we multiply the top and bottom by square root of 2 over square root of 2, then the numerator becomes square root of 14, the denominator becomes square root of 4, which is square root of 14 over 2. And that is rationalized. You can check on the technology to see that the square root of 3.5 is the same thing as taking the square root of 14 divided by 2. In problem 40, we are taking a look at that denominator, and really our goal is to get rid of the square root of 7. Now, the square root of 7 isn't a whole number, but you can see on the on your root chart that 7 can make 49. So if we multiply the top and bottom by square root of 7, which is like multiplying by 1 because this is 1, this is going to be 3 times the square root of 35 because 5 times 7 is 35, and 2 times the square root of 49. This means my numerator is still 3 times square root of 35, but my denominator is now 2 times 7 because the square root of 49 is 7. So this gives me 3 square root of 35 over 14. Now, this problem right here, we are now dealing with cube roots. And when we deal with a cube root, we can't just multiply by whatever the square, the root was in the previous problem. We have to do a little bit more thinking than that. Because if I take this 3 and multiply it by 3, it gives me 9, but 9 is not cube rootable. Now, on my chart, the next cubic rootable number that's divisible by 3 is 27. So if I just multiply the top and bottom by the cubic root of 9, that's going to get my 3 to become a 27. Now I don't have enough y's here to break out of the cube root, so I'm going to have to write this down as y squared. Y squared. So what this allows me to do is it allows me to, well, get the denominator up to the size that I need to break it out. Now my numerator is just going to get messy. 7 times 9 is 63, and x times y squared is xy squared. But remember, I don't really care about the numerator. I care about the denominator. 3 times 9 is 27, that was my goal, and y times y squared is y cubed. So I'm going to take the cubic root of 27, which is 3, the cubic root of y cubed, which is y. And so that gives me what I need in the denominator to not have any more radicals in the denominator. So for problem number 42, we're supposed to build this 2y squared up so it's perfectly cube rootable. Now the cubic root of 2 is not workable, but the cubic root of 2 can be built up to the cubic root of 8 if I multiply by 4. So if I multiply 4 times 2, sorry that doesn't look like a 4 there, 4 times 2, that makes 8. And y to the 7th, I need to get that into something that's divisible by 3. So I'm going to go with 2y's, and that will give me y cubed. If I go more than 2, it's going to give me something in the numerator that's going to need to get simplified. So here's where we're going to go. The numerator is now the cubic root of 12 x to the 4th y squared. The denominator is going to be the the cubic root of 8y to the 9th. So what that means is that my numerator, the cubic root of 12x to the 4th y squared, over 2y cubed, because the cubic root of 8 is 2, the cubic root of 9 to the y to the 9th power is y cubed. Now we have to do a little bit of more work when we have to rationalize or get all of these radicals out of these denominators, because we can't just multiply by a single term here. If I multiplied by the square root of 2, it would change the first one and then break the second one. So we're going to multiply by a binomial. Whenever you have a binomial, multiply a binomial. Choose the same binomial with the opposite symbol. This will simulate a difference of squares kind of problem that we had in our factoring lesson. So let me just focus right now on the numerator. If we do our distribution here, what we're going to get is we're going to get 5 square roots of 2 minus 15. Now if we do the FOIL of the denominator, we're going to get square root of 2 times square root of 2, which is square root of 4. Now, if I do this, I get negative 3 square root of 2, and if I do this, I get positive 3 square roots of 2. So the middle two terms simplify to 0 in our FOIL. So the F and the L of FOIL are the only ones that are going to be left. The O and the I got crossed out, just as I said them. And 3 times negative 3 is negative 9. So my numerator, I can just change the order there to fit my format. This will prep us for the quadratic formula chapter coming up next. And this is going to be 2 minus 9, which is negative 7. And there's an acceptable answer to problem number 43. So again, why did we multiply by a binomial? Because we had to get rid of the square root of 2. If we multiplied by a monomial, we would have had a square root of 2 given to the 3, and it wouldn't have solved our problem. But by squaring by the binomial with the opposite symbol, we get a situation where the O and the I cables cancel out, or simplify to 0, and then we're left with the F and L cable, which will be whole numbers. So for our last problem of the worksheet video, I want to take a look at this. We're going to have 4 plus square root of 5 instead of 4 minus square root of 5. So 4 plus square root of 5. Now again, in my numerator, we're just going to distribute, so this is going to be 20 plus 5 square root of 5. This will be my finished numerator. Now my denominator will FOIL. 4 times 4 is 16. 4 times square root of 5 is 4 square root of 5. Negative square root of 5 times 4 is negative 4 square root of 5, and again those simplify. And then when negative square root of 5 gets multiplied by positive square root of 5, we get negative square root of 25. Our numerator stays the same because there's nothing to do with it, just bringing it down. And this becomes 16 minus 5, which is 11. And that is the answer to that problem. And all of these were in your notes, and you can go and watch the videos on any part of these if you want to see a slower explanation of it in my earlier video series. But this ends a rather lengthy second part to our 3-part test prep review. So thank you for watching.